conduct two sessions. One is today, this one, and another session is on 19th. That is on Monday. So the areas that will be covered, we'll try to cover all the areas that I have in mind or study, sort of. The first area is the factor analysis, which consists of both the exploratory as well as confirmatory factor analysis. And for that, I will be using the normal IBM SPSS software that normally we use for academic and research purpose. And I have in mind to conduct one advanced models, which is called the K nearest neighbor analysis, for which I aim to use the IBM SPSS modeler. Modeler function, or the modeler version of SPSS, is slightly a different version. It has a different interface altogether. The kind of SPSS interface that you probably are seeing over the last few days in this workshop. It's almost like a spreadsheet kind of a configuration or an interface. But modeler function of IBM SPSS is slightly different, because it modeler function, it basically focuses on carrying out the advanced model function. Basically, it uses the machine learning, advanced machine learning, supervised and unsupervised learning. So if I get a time in the next session on Monday, I will be showing, because the functionalities and the kind of execution that takes place on the modular version of SPSS is slightly different, because in the normal IBM SPSS that we will be using today for factor analysis, particularly the exploratory part of the factor analysis, you will find that it pulls data, numerical data from certain data files, and then works upon it. So it has a very straightforward approach to data analysis, dealing with the data. But when it comes to the modular function, you will find, if I can show you, it is a linkage, or you can say interconnectivity with the widgets. So there are lots of widgets available in the drop-down menu, which actually builds up the model. So the job of the researcher is to drag and drop all the widgets in the working space and create a logical connection between all the widgets. And if a logical connection is created, the analysis automatically takes place at the back of the scene. So at the end of all the widgets being connected, you will get the final model if you click a run button. So that is one of the ways these days SPSS is used, mainly for the machine learning oriented, because analysis or model functions like the survey vector machine or random forest or any other kind of decision trees, or the scale and the nearest neighbor analysis, or artificial neural network, or any advanced kind of modeling techniques that we use. For those modeling, we are using this modular function. We have other softwares also, but SPSS has was this one. Anyway, what I will be focusing on today is basically the exploratory part of the factor analysis. And in the next session, basically, we will carry forward with the confirmatory part. So let's explore first, and then we can go ahead with the confirmation, because the confirmatory factor analysis will be using a plugin of the IBM SPSS that is called the AMOS, because IBM SPSS in itself is incapable to conduct the confirmatory factor analysis. So you require a different setup, a different plugin altogether for that using. Anyway, so this session is will be divided into two parts. One, a brief understanding about the factor analysis, because I believe that the audience or the participants are from different backgrounds. So some of you are well exposed to the multivariate techniques and the interdependent techniques like factor analysis, but for some it may be a new thing. Okay. So some theoretical aspects of the factor analysis, when to use it, why to use it, and what are the prerequisites or assumptions of deploying a factor analysis, the limitations of the factor analysis, and comparing the factor analysis with the other interdependent techniques. So it gives you a preferential choice about why to, apply EFA. So having understood some of the theoretical aspects of the factor analysis and the objective of using that particular analysis for your research purpose, then we will take up a small case study with a very small data set, and we will check how actually factor analysis takes place and what are the outputs of the factor analysis and how to report them and how to interpret. Because reporting and interpretation and reporting the factor analysis results, or as a matter of fact, any result that is coming from the SPSS platform is pretty important, because we have many standardized version of references. So we'd like to stick with those formats. So I will just take you through a very small presentation. The presentation will brief you out about certain theoretical aspects of the factor analysis, and after that we will take up the hands-on. Okay, I'm just switching off my video because let me share my screen first. So can anyone confirm whether the screen is visible or not?
Yes, sir, it's visible.
Okay,
Visible.
thank you. Okay, so let's start with the classification of the multivariate techniques. Normally, we classify multivariate techniques into two forms. One is the popular one, which is called the dependence method. So in a dependence method or in a dependence multivariate technique, it is appropriate when one or more of the variables can be either identified as dependent variables or and the rest is the independent variable. So we try to establish a kind of a relationship between the dependent variable and the independent variables, or even we can move one step ahead and try to find out any kind of a causal relationship. That means on the basis of the independent variable, can we predict the dependent variable? So we have several dependence techniques which are very popular for the quantitative researchers. And we use multiple regression analysis, we use the logistic regression analysis, we use conjoint analysis, the canonical correlation and discriminant analysis, we use the MANOVA, then SEM, the structural relation modeling, etc. All these are dependent techniques because in this particular method, the variables can be clearly categorized into dependent and independent. Side by side, we have another multivariate technique, which is called the interdependence method. So it is that multivariate statistical techniques in which a whole set of interdependent relationship is examined or explored. So no single variable is defined as either a dependent or an independent variable. So analysis of all the variables in the data set are taken up simultaneously. So what are the popular interdependence techniques that we normally find? Factor analysis, that is one of the areas that we will be focusing over these 2 days, particularly today. The cluster analysis is one of the interdependence technique. Perceptual mapping is a multidimensional percept of a certain construct or certain phenomena. If you want to have a clear-cut idea about a phenomena or a construct across multiple number of dimensions, then we use perceptual mapping. Multidimensional scaling or MDS is a very popular technique which is used for interdependence technique. Correspondence analysis is another. Correspondence analysis has become very popular with the qualitative researchers also these days, apart from being used by the quantitative researchers. So these are the set of interdependence techniques that we normally deal with. So if we have a total map of the classification of the multivariate techniques, if you just concentrate on the right-hand side of this particular diagram, so the number of dependent variables, if it is none, then we proceed for the interdependence methods, and we have all those analysis at our disposal. We have the factor analysis, we have cluster, we have perceptual mapping, we have multidimensional scaling, correspondence analysis, etc. So what is basically a factor analysis? Factor analysis is an interdependence technique whose primary purpose is to define the underlying factor structure among the variables which are observed in the analysis. For example, if we, this is a very bookish kind of a definition or a very theoretical definition. If I want to explain it with the help of an example, sometimes what happens, particularly the researchers who are from the field of social science. Myself, since I belong to the field of social science, I will be extracting some of the examples from the social science domain only. Say one particular person or one particular researcher is interested to measure, to have a measure about the emotional intelligence of a group of people or the emotional intelligence of an individual. Now, to measure the emotional intelligence of a particular individual or a group of individuals, unfortunately, we do not have a direct measure. It's very difficult to make a direct estimation or a direct measurement of emotional intelligence. Or as a matter of fact, if we take, for example, any other cognitive issues or behavioral issues, say, for example, someone is interested to measure the introvertness or the extrovertness of an individual. Okay? So he will not be able to measure it directly. So you have to adopt a surrogation technique. There has to be certain indirect way to measure those constructs. Okay, so you have to depend on certain observed, variables or certain observed manifestation of that particular individual or that particular group, which will lead you to certain, conclusion that this particular group has this kind of an emotional intelligence, or this group or this individual is introvert, or this individual or this group is extrovert, something like that. Okay, so on the basis of certain observed variables, normally we call them items or scale items. We can understand or we can identify the underlying factor structure, which is apparently invisible or apparently immeasurable. We do not have a direct measure for that. So the primary objective to conduct a factor analysis is to identify the underlying factor structure from the manifested variables or from the observed variables. So in a way, it is also a kind of dimension reduction or reducing the number of variables into a manageable proportion so that it churns out a very simple factor structure. So ultimately, my objective to conduct an exploratory factor analysis is to identify the factor structure from a given set of observed variables or from a given set of manifested variables. Okay. So if we expand this term exploratory factor analysis in a elaborative way, so it's a variable reduction technique that I have always already said that. Suppose you start with 30 to 40 variables, which are observed variables, and it's a way to compress all those variables into manageable proportion and allow the variables to load across certain extracted factors. So it's a variable reduction technique which identifies the number of latent constructs which are unmanifested or about whom we do not have a direct measure. Okay, or the hidden constructs, and the underlying factor structure of a set of variables, hypothesizes an underlying construct, a variable not measured directly, estimates factors which influence responses on the observed variable, and allows the researchers to describe and identify the number of latent construct of factors. That means for a particular, say behavioral aspect, as I told you, that it can be introvertness or extrovertness. Say, for example, introvertness, after observing a number of behavioral manifestations and getting data across those behavioral manifestations. Normally, what happens when you go for a factor analysis, you identify a set of scale items that will capture the behavioral aspect related to extrovertness or introvertness. Suppose you are measuring introvertness, one of the scale items may be like this, that this individual does not participate in group activity. So in a scale of say 1 to 5 or in a scale of 1 to 7, what will be the rank? Most, if you are agreeing with it, say the highest point of agreement, the scale value will be 7 or 5. If you are using a 7-point scale, it will be 7. If you are using a 5-point scale, it will be 5. And at the lowest, highest point of disagreement, it will be 1. So if you have a set of items, 25 to 30 items, which you are using to capture a single notion like introvertness or extrovertness, at the end of this factor analysis, you would like to find out that which are the manifested or observed variables that form this basic construct that you are trying to measure. So traditionally, it has been used to explore the possible underlying factor structure of a set of measured variables without, imposing any preconceived structure on the outcome. So what are the goals of EFA? Obviously, to help an investigator determine the number of latent constructs and to provide a means for explaining the variation among the variables using a few newly created variables or factors, and to define the content of meaning of factors, namely the latent constructs that we are talking about. So what are the assumptions underlying the EFA? First assumption that the observed variables that we are talking about, or the manifested variables that we are talking about, it should be taken up with the help of an interval or a ratio scale. There has to be a probabilistic sampling technique when you are dealing with the sampling plan, or when you are extracting samples from a given population, from a well-defined population. So non-probabilistic sampling, sample drawn with the help of non-probabilistic sampling, particularly convenience sampling or purposive sampling or judgmental sampling, it doesn't allow a researcher, it's not suitable in that the factor analysis on the basis of that. Relationship between the observed variables should be linear. That is one of the assumptions. Normal distribution, each observed variable, a bivariate normal distribution for each pair of observed variables, and there should be a multivariate normality. So these are the fundamental assumptions which governs the exploratory factor analysis. So the first one is when you are obtaining a data, you have to use either an interval scale, for example, a Likert scale, or a ratio scale. You have to depend on probabilistic sampling, for example, random sampling. You have to assume that the relationship between observed variables is very linear. The data is normally distributed, a bivariate normal distribution for each pair of observed variables, and you assume that there is multivariate normality. The conceptual assumption, you see, one of the basic issues in EFA is like this. When you are selecting the variable, the factor analysis is based on the basic assumption that there exists an underlying structure for the selected set of variable. But you see, it has to be grounded very soundly on theoretical basis. So it is the responsibility basically of the researcher to select that set of variables or items that are conceptually very valid and appropriate to represent the underlying dimension. Otherwise, you may get the statistical significance. The tests will be statistically very relevant, but it doesn't guarantee that the things that you are discovering or things that you are getting as an output is theoretically relevant also. So when you are selecting your variables, or when you are trying to, trying to visualize or trying to apprehend a factor structure, you need to be conceptually very valid. And this conceptual validity will come from a very robust study of the literature associated with the phenomena under study. So if you are studying emotional intelligence, make sure that you have studied enough literature to identify all the valid variables that were taken into consideration. If any given scale has been already used, you need to go through those scales also. If those scales are already tested, you can check on to the variables or the factors that were identified in that particular scale. So variable selection is one of the most critical things in case of EFA. So one of the conceptual assumptions is a solid grounding of the variables. And the second one is the sample homogeneity. The selected sample should be homogeneous with respect to the underlying factor structure. So, identifying the population and then creating the sampling frame and ensuring that each and every sample unit is inducted in that particular sample frame, and maintaining the homogeneity of the sample is very important in case of the EFA. There are certain limitations of the EFA also, although EFA, we consider it as a very robust, analysis for identifying those factors which are apparently invisible or apparently cannot be measured directly, or about whom we may not have a direct estimation. But there are certain inherent limitations. One of the limitations is the EFA is strongly based on the correlation. The basis of the factor analysis. It describes the relationships, but unfortunately, EFA doesn't draw on the causal inferences. So you cannot you cannot infer any causal inference out of the EFA results. The reliability of the measurement instrument is again, it's a matter of question. The internal consistency of the scale being identified, a lot of tests has to be conducted before you become very sure about the reliability and the validity of the instrument. The sample size is a question. Normally, we require a very large sample size to conduct an EFA. So minimal number of cases for reliable results is more than 100 observations and 5 times the number of items. So if you are having, say, a researcher has identified, say, 25 scale items or 30 scale items or 50 scale items. So if it is a 30 scale items, you need a minimum of 150 cases. That means 150 samples. And when you are conducting a quantitative research with the help of structured questionnaire, when you are going for extensive survey and your sample size is this large, there is every chance of missing data. Although nowadays we have several processes with the help of which we can ensure missing data imputation, it's not very good to have missing data in your data set. So to be on the safer side, if you require a minimum of 150 cases, you round it up with 200 subjects or 200 cases, so that all those cases with missing data can be deleted from the analytical frame. So the rule of the thumb is as far as the determination of the sample size or the requirement of the sample size for conducting an EFA is the number of items multiplied by 5. So if you have 15 items, it will be minimum 75, rounded up to 100 possibly. If you have 20 items, it will be 100, minimum 100. If you have 30 items, we have seen scales. For example, in 1985, there were 3 researchers by the name Parasuraman, Sitham, and Veri. They were trying to develop a scale about the perception of service quality. Okay, perception of service quality is such an intangible issue. It was not possible for the social scientists up till then to have a direct measure of the service quality, because it perceptually differs from one particular individual to another. So these 3 gentlemen came together to try and develop a particular scale. And initially, when the scale was formed in when they proposed the scale, the name of the scale is SURF-12. So when they proposed the scale for the first time in 1985, there were 125 items. So with 125 scale items, the minimum number of sample size that was required was 625. So in any case, they conducted a survey in multiple locations with huge number of sample size. But this is just an example. In subsequent times, what happened? The scale got refined and refined based on multiple number of studies. In 1988, the scale got refined and the number of scale items came down from 125 to 85. In 1992, the scale got further refined and the number of items came down from 85 to 50. In 1996, the scale got refined and the number of items came down to 50 to a manageable 30. So now when we are using SURF-12 for industry survey or consumer survey, we are using a battery of items. The number of items is 30. So we prefer to take almost 200 to 250 number of sample size to conduct a survey on the perceptual elements of service quality. So that's how a scale can be developed on the basis of exploratory factor analysis. And there is a provision that repeated, when you are going for repeated refinement of a particular scale, you may find that certain observed variables may be very obsolete or redundant. I will show you during the analysis that how you will come to a conclusion that certain observed variables or items can be deleted from your final scale measure. Okay. Anyway, sample selection again is one of the limitations because it is only representative of a population, and most importantly, it do not pool the population. Variables could be very sample specific, namely a unique quality possessed by a group does not generalize to the entire population, particularly those social researchers or researchers from the domain of social science who are working on specific ethnic community or a specific community or a group of individuals where the items or the variables are very specific of that particular group or population or community. It becomes very difficult. Even suppose someone is doing a research on the tribal community in West Bengal, it will be very difficult to extrapolate the result on each and every tribal community in India. So it has that kind of a limitation also. Now, you have often come across a term called the principal component analysis. Principal component analysis, operation-wise, concept-wise, is almost similar to that of the exploratory factor analysis. We will see when we will be dealing with the data and the SPSS platform. There are certain similarities. There are similarities also. Similarities basically, you know, they actually reduce the number of observed variables. Okay, and they are based on correlated observed variables. The entire, you know, theme or the entire posit of both these analysis, it depends very strongly on the correlated observed variables. The sample size requirement to conduct PCA and EFA are both same. The rule of the thumb, that is number of items into 5 times, it's the bare minimum requisition. PCA and EFA. Measures of adequacy, sample size adequacy are both same in PCA and EFA because both of them uses the KMO measure of sample adequacy. In both the cases, analysis of factors requires decisions regarding factor retention, the rotation of the factors, and the interpretation. But there are certain differences. You know, in case of PSA, it models the total variance. In case of EFA, it measures or it models only the common variance only. Okay, so the concept of unique variance is absent in case of the PCA. Sorry. In PCA models factors in terms of observed variables. In case of EFA, models observed variables in terms of factors. In principal component analysis, the primary objective is typically to reduce the data. In EFA, yes, data reduction or the variable reduction is one of the objectives, but it typically tries to identify the latent factor structure. Okay, so PCA, you know, its sole objective is to reduce data to create a kind of data distribution which is manageable by the researcher. But in EFA, basically the researcher's objective is to identify how the observed variables are clubbed into certain unidentified factors. So they are much more interested to identify or to locate these unmanifested factors or the latent factors. You know, criteria for extracting the factors. We talk about extraction of the factors because one of the fundamental jobs of the exploratory factor analysis is the extraction of factors. So the first criteria for extracting factors is known as the Kaiser's criterion. The Kaiser's criterion, it was suggested by Guttman, Guttman, and it was later adopted by Kaiser. It considers factors with a unique eigenvalue. Eigenvalue, we will have a look into the concept of eigenvalue and eigenvector at a later part of this particular presentation. So it considers factors with an eigenvalue which is greater than 1 as the common factors. That's one of the criteria for extracting the factor. Then we have the second one is called the Cattle's scree test. So what is a Cattle's scree test? Actually, the name is based on an you can say analogy between the debris called the scree. Actually, what kind of a debris? These debris that collects at the bottom of a hill after a landslide, and the relatively, what is the analogy to the EFA? In the EFA process also, we find certain factors meaninglessly extracted due to over extraction. So these are actually the debris or the waste, okay, or the scree. So on a scree plot, because each factor explains less variance than the preceding factors, we draw an imaginary line, connecting the marks for successive factors. And, generally, it starts from the top left of the graph. I will show you the graph of the screen. You will find it starts from the top left of the graph and it ends at the bottom right of the graph. And there is, in some point of that particular curve, you will find an elbow or a kink. Okay, sometimes it is called kink, K-I-N-K, but typically it is also known as elbow. So anything Cattle's guidelines, it says that any factor which is above this elbow or above these kink are to be retained as the final factor structure, and any factor which is lying below this particular elbow or below this particular kink are to be discarded or to be removed from the final factor structure. Then we have the proportion of variance, which is another criteria for extracting factors. The proportion of variance accounts for, basically we consider it keeps or retains a factor if it accounts for a predetermined amount of variance, say for example 5% or 10%. And the last one is the interpretability criteria. The interpretability criteria of the EFA, on what basis we are interpreting? We are interpreting on the basis of communalities being extracted. We are interpreting on the basis of the rotated factor matrix that is extracted. We are interpreting on the basis of the total variance being extracted. So there are a number of indices, there are a number of parameters based on which the EFA interpretation is done. This is what the EFA model looks like. It almost looks like a regression model. Y is equal to x lambda plus E. So Y is basically the matrix of the measured variables. X represents the matrix of the common factors to be extracted. Lambda is basically the matrix of the weights or the factor loadings. So factor loadings are nothing but the correlation coefficient between the items or the observed variables and the extracted factor. And E is basically the matrix of the unique factor. Sometimes it's also known as the error variation. So we have the initial extraction, the each factor. If we go for a stepwise understanding of the EFA, we go for the initial extraction. Each factor accounts for a maximum amount of variance that has not previously been accounted for by any other factor. So once we perform this SPSS test, all these steps which now looks very theoretical and difficult to understand, then it will be explained. But since we are dealing with a little bit of theory governing the EFA and how the EFA is conducted, what are the steps being followed, let us have a slight understanding about this, but more categorically, or we will understand with more clarity when we will be dealing with certain practical data. So initial extraction, each factor accounts for a maximum amount of variance that has not previously been accounted for by any other factor. And the factors are uncorrelated. Normally, it is said that EFA is basically a transformation of a highly correlated observed variables into a linear combination of uncorrelated factors. But again, that is also an issue which deals with what kind of model the researcher is proposing. The researcher may think about a model whereby the extracted factors may remain uncorrelated after the extraction, or the researcher may also think about a model whereby the extracted factors are correlated. So what kind of rotation will be used, that will be determined on the basis of what kind of model the researcher is having in their mind. Okay, so the researcher can have this kind of a model where the factors, the extracted factors or the latent factors or the unmanifested factors, or we can say overall the factor structure will be a combination of factors which will have correlationship with them. Normally, what happens when we extract factors, we assume factors to be uncorrelated with each other. So eigenvalues represent the amount of variance accounted for by each factor. Now, the variance in EFA, this is one of the most important thing, or one of the most important issues, or one of the most critical issues that we see in the exploratory factor analysis, the variance issue. You know, there is a partitioning of the variance in factor analysis. Since the goal of factor analysis is to model the interrelationship among the items, we focus primarily on the variance and the covariance rather than the means. So factor analysis assumes that variance can be partitioned into two types. One is the common variance. How to define a common variance? You can say that common variance is the amount of variance that is shared among a set of items. Items that are correlated will share a lot of variance. Okay. And we have another concept which is called the communality, which is represented by H square. Is a definition of common variance that ranges from basically 0 to 1, and values closer to 1 suggest that the extracted factors explain more of the variance of an individual item. Okay. Now, the other part of the variance is the unique variance. Unique variance is again divided into two. One is called the specific variance and one is called the error variance. So how to define the unique variance? So unique variance is any portion of the variance that is not common. Okay, so we have the common variance in place. So two types of unique variance can be seen. One is called the specific variance, specific to a particular item or a scale item or to an observed variable. And the error variance comes from the errors of measurement. It's as simple as that. And basically anything which remains unexplained by the common or the specific variance. So the total variance is basically a summation of the common variance and the unique variance. Okay. Now, here comes the difference between the PCA and EFA. In case of a PCA, the total variance is equal to the common variance. The PCA does not have that particular partition of the unique variance. So in case of a PCA, the total variance is all about the common variance. Okay. In case of an EFA, we have the unique variance in place also. Okay. So this is all about the variance, because the reporting of the variance and the interpretation of the variance, it's very important. Okay, so little bit about the factor extraction. We can talk about the factor extraction a bit later. So let us continue with this. So continuing with the EFS steps, the second step is to determine the number of factors to be retained. This can be done by checking the spree test, as I have told you, looking for the elbow or the king. The factors which are above the elbow or above the king are to be retained as far as Cattell's observation, and the factors which are lying below the elbow or below the king are to be discarded. Look for the proportion of variance. We normally look for the total variance explained by the factors. And the interpretability takes into consideration 4 issues. Number 1, at least 3 observed variables per factor with significant factor loading scores. Now, this particular logic, we will try to understand when we will take up confirmatory factor analysis. How many observed variables per factor? Because a lot of scholars, a lot of students are having this question in their mind, that to define or to interpret a particular factor or to identify a particular hidden factor, how many items are required? Say a particular factor is defined with the help of 2 items, and a particular factor is defined with the help of 4 items. In both the cases, the item loadings or the correlationship between the items and the factors are very significant. Which particular model will be much more robust or much more, acceptable? You see, the minimum number of items that we require par extracted factor is 3. If it is greater than 3, say if it is 4 or 5, it is an over-identified model. If it is 3, it is a just identified model. If it is lesser than 3, that means 2 items or 2 observed variables par extracted factor. It is an under-identified model. Under-identified models are not good models. Yes, there will be statistical significance. You will touch the statistical significance level. But unfortunately, the model will not be very sound, model will not be very robust. Okay? Interpretability on the ground of common conceptual meaning, interpretability on the ground of measuring different constructs, and the rotated factor pattern has very simple structure, no cross loadings. Okay? So that particular issue of this under-identified, just identified, and over-identified model, and this cross-loading of this observed variables into factors, these two will be explained in much more detail when we will take up the CFA, the confirmatory factor analysis. So there is also a concept which is called the rotation. We will talk about this rotation once we take up the data analysis, and then we come to the interpretation of the solution that comes through the exploratory factor analysis. Now, performing the exploratory factor analysis, it is basically accomplished in 2 steps. Step number 1 is the factor extraction process. The factor extraction process can either be done with the help of a PCA, which is not our point of discussion today, but PCA is one of the ways with the help of which factor extraction can be done. And number 2 is the common factor analysis. Okay. So these are the 2 approaches to factor extraction, which actually stems from the different approaches to variance partition. Okay, one is PCA and common factor analysis. So in case of PCA, unlike EFA, exploratory factor analysis, PCA makes the assumption that there is no unique variance that we have already seen. So the entire total variance is calculated or computed on the basis of the common variance. Okay, so the total variance is equal to the common variance. Additionally, if the common variance is equal to 1, then the common variance is equal to the communality. Okay, so this is one of the unique features of PCA, which makes it absolutely different from that of the common factor analysis. The common factor analysis is used for the EFA, the exploratory factor analysis. Okay, so in case of factor extraction, let me repeat this. We have 2 possible solutions. One is to conduct the PCA. PCA will be a very restrictive kind of a factor extraction, and there we will be extracting certain principal components, but the basic objective of the PCA will be to reduce the number of observed variables. So it's basically a dimension reduction process. Now, in case of a common factor analysis, the partitioning of the variance, it differentiates from the PCA. Okay, because in case of a PCA, what we have seen that the total variance is equivalent to that of the common variance. So both the methods, actually, this PCA and common factor analysis, both the methods, they try to reduce the dimensionality of the data set down to, you can say, a fewer unobserved variables. But whereas the PCA assumes that the common variances takes up all the total variances, CFA assumes that the total variances can be partitioned into 2. We have already seen this. If we can go back and just take a look over here. CFA assumes that the total variance can be partitioned into 2. One is called the common variance and the second one is called the unique variance. The unobserved or the latent variable that makes up the common variance is called the factor. Okay, let me just repeat this. The unobserved or the latent variable that makes up the common variance is called the factor, and hence the term factor analysis. Okay, so the unobserved or latent variable that makes up the common variance is called the factor that we are looking for, or that we are trying to identify the underlying factor structure, and hence the name factor analysis. The other difference between the PCA and EFA is that basically lies the goal of the analysis. So if your goal as a researcher is simply to reduce your variable list down to a very linear combination of smaller components, then go for PCA. Okay. However, as a researcher, if you believe that there is some latent construct that defines the interrelationship among items, then EFM will be much more appropriate. Okay. So it ultimately boils down to what is your objective with regard to the analysis. Okay. The next one we talk about is the factor rotation. And factor rotation is a very interesting thing in exploratory factor analysis, because factor rotation ensures unidimensionality and number two, interpretability of the solution. Otherwise, if we are not conducting the rotation process, sometimes the outputs are so jumbled up, it doesn't offer as a very good interpretable solution. So factor rotation can be of two types. Number one is orthogonal rotation, and the number two is an oblique rotation. So what is basically an orthogonal rotation? Without going much into the technicalities of these things, orthogonal rotation, it assumes factors that are independent or uncorrelated with each other. So if I go with an orthogonal rotation, the x-axis and the y-axis, if we consider that these two represent two factors, say x-axis is representing factor 1 and y-axis is representing factor 2, the orientation of the x and the y-axis will be 90 degrees with each other. So any kind of a rotation, any kind of a tilt will maintain this 90-degree relationship between factor 1 and factor 2, or between the x and the y-axis. Now, what is an oblique rotation? Oblique rotation, in case of an oblique rotation, factors are not independent and are correlated with each other. Now, see, important thing is, when you will be conducting the factor analysis, both these options will be put forward to you. Either you select orthogonal rotation or you select an oblique rotation. So there are logic based on which you will be selecting either orthogonal or oblique. You see, if my objective is to identify a factor structure or identify a group of factors whom I want to remain uncorrelated with each other after the extraction, then I will go for orthogonal rotation. So I want to identify unique factors which will not be intercorrelated with each other. So say I have 5-factor structure. All the 5 factors will be independent, will be very unique, and they will not share any kind of relationship with each other. But as a researcher, if I believe in a model which requires a factor structure support and which requires the factors to be intercorrelated with each other even after the extraction, then I will select the oblique rotation. Orthogonal rotation will ensure zero correlationship between the extracted factors. Oblique rotation will ensure correlationship with the factors after the extraction. Okay, so you see, this is almost like a you can say a graphical representation of what happens actually in a factor rotation. On the left hand side of your picture, you see the x and the y axis. They are denoting factor 1 and factor 2 respectively. So on x axis we are plotting factor 1, and on the y axis we are plotting factor 2. And we have 5 observed variables, as you can see here: x1, x2, x3, x4, and x5. And we have, sets of values for x1, x2, x3, x4, x5 that are loaded in factor 1 and factor 2. So x1 with factor 1, this is the correlation value, it's 0.4. x1 with factor 2 is 0.6 now. Now, you see the difficulty of a researcher. Each and every observed variable has to be assigned very specifically to a single factor. So there cannot be a sharing of observed variable across multiple factors. But the problem with the model in the left-hand side, where the rotation has not been done, is, see, the first observed variable x1, it is correlated with factor 1 and the correlation coefficient is 0.4. And with factor 2, it is 0.69. And both these coefficients are highly significant. Okay, so it is very difficult for the researcher to interpret where they will be going to assign x1. Should they retain x1 as a factor 1 variable, or should they retain x1 as a factor 2 variable? So, unidimensionality is a big issue over here. Interpretability becomes a big. The same thing happened in case of x2 also. Same thing happened in case of x3 also. So it's very difficult. In both the cases, the factors have loaded. The observed variables have loaded into the factor, and these loadings or the lambda values are very significant. So it's a dilemma or a confusion for the researcher, which item to be retained for which factor. So the software, the SPSS, it creates a kind of a tilt of the axis without disturbing the angular relationship between the axis. You see on the right hand side of the picture, the particular axis has been rotated in a clockwise direction. Even if it is rotated, even after the rotation, the F2 and F1 they are retaining. It has been. The F2 and F1 has retained the 90-degree angle. Now you see the interpretation. Since the axes have rotated, it gives a better interpretability of the observed variables. Now we can easily say that the observed variable x1 is much oriented towards the factor 1. The observed variable x4 is much aligned with the factor 2. The observed variable x5 is much oriented towards factor 2. So it gives us a better interpretability. So when we are going for this factor rotation, particularly if we are going for this orthogonal rotation, in orthogonal rotation, one of the characteristics of orthogonal rotation that I have told you, that even after the rotation, the angular relationship between the x-axis and the y-axis, it remains at 90 degree. The fundamental difference between the orthogonal and oblique rotation is, in the case of an oblique rotation, this angular relationship between the x and the y-axis, it is not mandatory that it will be 90 degree, or even after rotation, they need not maintain a kind of a similarity with the pre-rotation angular relationship. In the output of the EFA, you will find one particular matrix as an output, which is called the factor transformation matrix. We will show when the data analysis will be taken up. In the factor transformation, we get as an output the factor transformation matrix. The factor transformation matrix can also tell us the angle of rotation. If we take the inverse, cosine of the diagonal element, factor transformation matrix, it's a matrix of the values of the factor loadings. And if we take the inverse cosine of the diagonal element in that particular matrix, it will give us the angular tilt, what amount of tilting is required. Okay. So as far as the rotation, concept of rotation is concerned, let us stick up to this, because now let us go to I will come to this later, this particular graph. Let us take an example, then we will try to understand on the basis of the analysis, or on the basis of a practical, we will try to understand more about the EFA. So this is a very small example with a very small data set. The example is, this is a hypothetical example, not a part of a empirical research. So consider a construction company, which is a very hypothetical company, say ABC Builders, that is planning to build an apartment in a complex near a university. And suppose the company is interested in identifying the perception of the university faculties regarding the value consciousness and the price consciousness and the purchasing decision involvement and sale proneness that would help the company to construct and design the apartments according to the target people. Now you see the kind of dimensions or kind of factors that the researcher is taking into account, like value consciousness, or price consciousness, and purchase decision involvement, and sale proneness. These parameters are very difficult to measure, to have a direct measure. It's very difficult to estimate these parameters directly. So you need some kind of an indirect measure. So a lot of observed variables are required, a lot of statements required that will adequately capture the notion of these factors. Okay? So these are the four, you can say, latent factors: value consciousness, price consciousness, purchase intent, decision involvement, and the self-proneness. Okay, the company hired a marketing research firm to determine how these four major response dimensions the faculty is concerned about before buying an apartment. So the research firm identified the scale to measure these four constructs. These four constructs, it's better to say latent constructs because they are not manifested yet, using some kind of an existing literature in price consciousness. So the researcher is using a 3-item scale. And for value conscious, it's a 3-item scale again. For sale proneness, it's a 2-item scale, and for PDI, it's a 4-item scale. Now, when I say item, what basically is item? So items basically are the statements, okay? Statements against which you will be generating the response. Statements which are supposed to capture the notion of the latent construct. So if there are 3 items, that means there are 3 statements which are supposed to capture or which are supposed to explain value consciousness. When I say 4-item scale for PDI, these are the 4 statements against which I will be generating the response from a group of people or from a group of university teacher, which will probably project their purchase decision involvement or the PDI. So in total, 3 plus 3 plus 2 plus 4, there are 12, observed variables or 12 items. So the firm surveyed 98 randomly selected respondents. You see, the minimum number of sample for this particular study required was 12 into 5, 60. So when we are conducting a survey with 98 randomly selected respondents, I think it's more than enough. Okay, so it will cover up for the missing data if it is there. So the firm surveyed 98 randomly selected respondents, all are faculty members, using different scales to determine the perception of the faculties with regard to the PDI, the price and value consciousness, and the self-proneness. So this is the case. And now let us see the data. We will have the data first. I'll look into the data. This is the data. So if we go for the variable view, I was talking about the statements. You see these kind of statements. These are the statements. So when you are fixing up the label, let me show you the data view. Since I told you that there are 12 variables, as you can see. In the variable view, it will be clear. Variable number 1 to variable number 12. And for each and every variable, the statements are placed as a label. Okay. Say, for example, variable number 1, one of the statements for variable number 1 is selecting from many types and brands of this product. Here, the product means apartments available in the market. So this is the entire question. Do you think that the various types of brands of these products available in the market are all very alike or all are very different? So these are the statements which will capture the notion of the 4 constructs that we have in mind. Okay, so this is the data that we have from 98 research participants, and fortunately we do not have any missing values. Okay, so to do a factor analysis, before doing a factor analysis, we can do one thing. We can check very quickly the reliability of the scale. That's the internal consistency of the scale, and we know there is one particular parameter. There is one particular indices which, with the help of which we can check the internal consistency of the scale, which is called the Cronbach's alpha. So the alpha value we can say. So we go to analyze over here. Okay, we come to the scale and you click reliability analysis. By default, it will take up this alpha value. So we are basically checking the alpha, not the other reliability analysis score like split up or Plattman, etc. So we are checking the Cronbach's alpha, and you select all the items over here, and you transfer all the items in the right hand side window, and not required. You need not check any other statistics because we are only interested to check the alpha value. So if we click OK, we will get the Cronbach's alpha value. The Cronbach's alpha value is 0.838. So any Cronbach's value which is greater than 0.8, it signifies that the scale has certain internal consistency and is a reliable enough scale to proceed with your factor analysis. Okay. So with the help of this particular data set, let us go ahead and conduct the factor analysis. So in case of a factor analysis, what we need to do is to go for clicking this analyze button. And you see, factor analysis basically is a concept of reduction of the dimension. So over here, categorically, you will find one particular item which is called dimension reduction. So you come over here and then click factor. Okay, you see, initially, since I was trying with this data, initially by default, these factors will be on this side of the window. So you are required to select all these and transfer it over here. Okay, so that's the primary function that you need to perform, and then you have a number of things to check. So the first one is the set of descriptives that you want to check or that you want to analyze. So over here, I specifically require you can check on the univariate descriptives. It will give you all the descriptive analysis of the data. You can look for an initial solution. Anyway, it's not that important because you will not be reporting in your journal paper. But two things over here are very important. One is the determinant score, the correlation determinant, which you need to report. And the second one is the KMO, the Kaiser-Meyer-Olkin test report, and the Bartlett's test of sphericity. These two are very critical and important tests to be reported for factor analysis. And both these tests are having certain objectives. Okay, so KMO has a specific objective, and Bartlett's test of sphericity also has a specific objective. So make sure that you check both these boxes. So continue. Extraction. Now, if you are interested about only dimension reduction, then you select. See this particular method box. It will open up a number of methods for you. If you are only interested about dimension reduction, you go for the PCA. So it will conduct a PCA for you. But if you are interested to find out the underlying factor structure, so you select this one, the principal axis factoring. Apart from these two, there are maximum likelihood model or the generalized least squares, unweighted least squares. So each and every model can be adopted based on what you want to achieve or what is your objective with the overall model that you are trying to develop. So since we were interested to go for an EFA, we are going for the principal axis factoring. Now over here at the very bottom, you will find when you will be conducting EFA, this maximum iteration for convergence, by default, the value will be 25. Okay. But in most of the cases we have seen, since we are dealing with very large data sets to conduct the exploratory factor analysis, sometimes you will find the iterations are converging after 78 iterations, 80 iterations, 56 iterations, etc. So it is better to be on the higher side, make this maximum number of iterations to 100 for the convergence. Okay. Now over here, what we want to display, we want to display the scree plot. Okay. If you want, you can have the unrotated factor solution also to have, since we are having a kind of a demonstration, so we are going for the unrotated factor solution. But when you will be writing a paper for the journal and you will be using this particular analysis, unrotated factor solution is not required for uh, for going for this one reporting. We are continuing, going for rotation. Okay, so we are going for orthogonal rotation. So orthogonal rotation, what are the orthogonal rotation that we have over here? There are a few types of rotations which we can use. One is the Varimax rotation. By default, you will find the Varimax rotation will be selected. Okay. And then there are other rotations also, like Vertimax rotation, Equamax rotation, Promax rotation, direct oblique rotation. So you have a number of options. But some of the rotations are orthogonal, some of the rotations are oblique rotation. So you need to know which of the rotations are orthogonal. Since if you are interested with the model which will churn out factors which you want that the factors will stay uncorrelated with each other even after the extraction. So you need to choose the orthogonal rotation. So everything is determined on the basis of the model in your mind. If your model is having an uncorrelated factor structure, you have to go for orthogonal rotation. If you are going for orthogonal rotation, Varimax rotation or the Varimax type is one of the orthogonal rotations that you can choose. So as I've told you, that Varimax is one of the popular orthogonal rotation. So what it does actually, it maximizes the variances of loadings within the factors while maximizing differences between the high and the low loadings on a particular factor. Okay, and this Varimax achieves a very simple structure that is very much desirable for a researcher. But having said that Varimax is quite a popular orthogonal rotation, and in most of the cases the researchers are using it. It is not as good for detecting an overall factor, because what it does, it splits up the it splits up the variances of major factors among the lesser ones. Okay, so if you want to have a much more robust understanding about your model with a very prominent factor loadings, that means the correlation score between the observed variables and the extracted factors, if you want them to be significantly on the higher side compared to that extracted by the Varimax rotation, you can opt for another orthogonal rotation, which is called this one, the Quartimax rotation. Okay, the Quartimax rotation is another example for orthogonal rotation. So we can say that the Quartimax may be a better option for detecting an overall factor. What Quartimax does, it actually maximizes the squared loadings so that each items loads most strongly onto a single factor. Okay, so Quartimax, if I compare it with a Varimax, it gives you a better chance to make your model more strong. And then we have another orthogonal rotation amongst these options, which is called the Equamax. Equamax is nothing but a hybridization between the Varimax and the Quartimax. And in most of the cases, Equamax is not recommended at all. So that leaves us with two options. One is called the direct oblique and one is called the Promax. Direct oblique and Promax, these two are oblique rotation. So if your intention is to ensure correlationship between the factors, even after the extraction, you can go for either direct oblique or Promax. If you are going for this oblique rotation, you will have certain unique metrics which is not produced by the Varimax rotation. Anyway, let us stick with this Varimax rotation for the time being, and I'm just converting this maximum iteration for convergence to 100, and I'm continuing, and I'm going for the scores. I'm not doing anything over here. So because if you are interested at a later stage to go for the factor scores, you can use either regression or the Bartlett or the Anderson-Rubin test. But since we are not interested at this particular point of time, we are not disturbing this particular area. So let it be like this only. Then we go for the options. Okay. In options, let us uncheck this particular box which says suppress the small coefficient. For the time being, we are not using this, and we are using this particular check which is sorted by size. So it will be, from the higher factor loadings to the lower factor loadings. So continue. So everything is set. So we can click on OK and wait for the analysis to take place. You see, these are the descriptive statistics. So you have the mean, standard deviation, and this is our sample size, the n value. So we have mean value for each and every item and standard deviation. Let us start with this correlation matrix, because we start reporting, the factor analysis from the determinant value. Okay, the determinant of the correlation. Why it is important? You see over here, the determinant value is 0.007. You see, one of the assumptions, fundamental assumptions of factor analysis is that the observed variables, how many observed variables we are having? We are having 12 observed variables. So the first set of analysis is the correlation analysis between these 12 observed set variables. So the underlying assumption of factor analysis or exploratory factor analysis is that the observed variables will share high degree of correlation with each other. Okay, so the determinant of correlation is very important. So in general, the determinant of correlation matrix, it can range between 0 and 1. So all the off-diagonal values that you see here, the off-diagonal values, if it becomes 0, equals to 0, the determinant of that matrix then becomes equals to 1, and hence it assumes an identity matrix. Okay, so if the off-diagonal values that we get here, if it is equal to 0, the determinant of this particular matrix becomes 1. So it is one of the extreme values of the determinant. As I have told you, that the correlation matrix, the determinant of the correlation matrix, it ranges from 0 to 1. So if it assumes a value 1, then it becomes an identity matrix. Now, if there is a 0 correlation between the items, it signifies. Therefore, the factor analysis will produce as many factors as there are items. So if it is a 0 correlation, so there will be 12 factors being extracted. Okay, so there will be no reduction, or so no reduction in the dimension. Now, if the opposite thing happens, if the determinant value is 0, it means that there is at least one, linear dependency in the matrix. So when this occurs, you will find the SPSS will issue a warning. Okay, and the warning will come over here, Okay, if the determinant value is 0, there will be a warning. What will be the warning? The warning will be like this, that this matrix is not positive definite. Okay, but in this particular, if it is like that, if the determinant is 0, then the matrix is known as a singular matrix. So there are two aberrations, there are two problematic correlation matrices that we may have to face with in extreme cases. One is the identity matrix, and the second one is the singular matrix. And it becomes very difficult for the next set of test. Okay, let us come to the next set of tests. But fortunately, in our case, you see the determinant value is 0.007, which lies between 0 and 1. The value lies between 0 and 1. So it's not a problem. We do not have a singular matrix or an identity matrix to deal with. Okay, so the next set of test is called the KMO and the Bartlett's test. What is a KMO test? The full form of KMO is Kaiser-Meyer-Olkin. It's basically a measure of sample adequacy. So KMO value, if it is greater than actually 0.6, so we consider that the sample is adequate. But to be on the safer side, and normally accepted standard of a KMO value these days is greater than 0.8. So in this case, we get a 0.806. So we consider that we have achieved sample adequacy. In any case, we have sample adequacy, isn't it? Because we consider 12 scale items, and 12 into 5, we required a minimum number of 60 samples, but we conducted the study with the help of 98 samples. So in any case, sample adequacy was achieved. Now, what is this Bartlett's test? Because Bartlett's test of sphericity churns out the chi-square, okay, with the degree of freedom and the significance value. Now, Bartlett's sphericity test, it actually tests the null hypothesis. What is the null hypothesis? The null hypothesis is there is no relationship between the items, no relationship between the observed variables. That means what? That means the correlation matrix is an identity matrix. That means all the off-diagonal values are 0. Okay. So if we get a high chi-square value, that will help us to reject the null hypothesis. Rejecting the null hypothesis means there is no relationship between the items, that will be rejected. That means we are accepting that there is a high degree of correlationship between the observed variables, which is one of the essential assumptions of EFA. Okay. So the approximate chi-square value over here is 452.251, which is sizable enough, and the degree of freedom is 66. So we are in a position to reject the null hypothesis that that there is no relationship between the items. So this particular data set that we are having, or rather this particular correlation matrix that we have got for ourselves, is neither identity matrix nor a singular matrix. So we can go ahead with the rest of the data analysis. The rest of the data analysis, it focuses on the technical outputs like the communalities, which is a part of the variance. Then we have the totals variance explained. And then we have the factor matrix, we have the rotated factor matrix, and then we have the factor transformation matrix. Now, how these calculations, since this is a software generated calculation, you need not actually, if you are not from the field background of statistics or mathematics, you are not supposed to know how these calculations are taking place. Okay, since you are using the software as a tool to support your research work, only thing you have to do is to interpret. Now, you see one interesting thing over here. What would have been the difference between, we have used principal axis factoring over here, isn't it? When we did the analysis, let me go back over here for the extraction. You see, we have gone for the principal axis factoring. Had we, opted for the principal component instead of principal factor, because principal axis factoring is basically conducting an EFA. If we are using this principal component as a method for factor extraction, it will be a PCA, or the principal component analysis. If we do that, what will be the difference? See, every other thing remaining the same, if we are simply changing the method of factor extraction, and say if we are clicking continue, okay, so what will be the difference? The difference will be visible in the communality value. You see the communality over here, the initial value is set as 1. Okay, the initial eigenvalue is set as 1 when you are going for the principal component analysis. But when you are using a principal axis factoring, you see the communality value, the initial value is never set as 1. Okay? So it has assorted value. So that is one of the differences in the communality. See, in case of PCA, we said that the total variance is equal to the common variance, because PCA does not have this particular component called unique variance. Okay. And if the total variance is equal to 1, it becomes equal to the communality of that. So, communality 1, it actually depicts the total variance of the factors that were extracted through principal component analysis. Okay. So that particular difference between the PCA method applied for the extraction of the factor and the principal axis factoring applied for the extraction of the factor is visible if we on a very prima facie basis, there are other differences which will be evident from the output, but on a very prima facie basis, we can identify the differences on the basis of the communality values, the initial communality that have been extracted. Okay, now it will be very interesting to know how these communalities are estimated. Okay, how we are getting these figures like extraction of the communalities, how we are getting this. Okay, how we are getting this total variance explained. So let us see the scree plot first. I told you when we explained theoretically the scree plot. The scree plot starts from the left-hand top corner of the graphical plot. See, it starts from here and it ends on the right bottom corner. Okay. Now you see the eigenvalue which was set for the extraction, the eigenvalue set for the extraction was 1. So the minimum eigenvalue accepted for this particular factor structure solution is 1. So anything, this is what we call the elbow. From here, the actual kink is starting. Okay, from this particular value 1. So what Cattle has suggested that all such factors that appear over this particular elbow or over this particular kink are to be retained, and all such factors below this kink are to be discarded or removed from the factor solution. So you see how many factors can be retained? 1 over here, 2, 3, and 4. So it's basically a 4-factor solution. We got a 4-factor structure. Okay. So let us see the total variance extracted. Over here, you find the total variance explained. You see, the total variance explained by 4-factor is 57.68% over here. And there are 4 factors, 1, 2, 3, 4. These 4 factors are explaining a cumulative total variance. This is the rotation sums of squared loadings. So the rotation sums of square loadings, the cumulative variance being total variance being explained is 57.68%. And it is explained by 4 extracted factors. Okay. So the scree plot actually justifies that we can consider this as a 4-factor solution. Now, I just stopped over there in your presentation. I said that we will be looking into this at a later point of time. Now, this one, let us see. This will explain how these calculations are done, particularly for the communalities, etc., etc. So let us see. Let us see the entire relationship. Then I will explain how these calculations are taken. So the first one, squaring the elements in the factor matrix, it will give you the squared loading. So if you sum up the square each of the element of this factor or component matrix, it will give you the squared loadings. Then summing the squared loadings of the factor matrix across the factors give you the communality estimate. So let us go to the data over here. Over here, summing the squared loadings of the factor matrix across the factors. So square of this plus square of this plus square of this plus square of this will give you the communality estimate. Okay. So let me just repeat. Summing the squared loadings of the factor matrix across the factors gives you the communality estimate. So square of this loading, square of plus square of this loading, square of this loading, square of this loading, you will get the communality estimates. So what is given over here, okay, or extracted there. Now the third one, come to here, this one, okay. Summing the squared loadings of the factor matrix down the items gives you the sum of squared loadings in case of principal axis factoring, or the eigenvalue in case of the principal component analysis. So again, let us go back to the data. This time what we are doing is the sum of the squared loadings of the factor matrix. So square of this, square of this, square of this, square of this, square of this. So you add all the square of these individual factor loadings and then you will get the sum of the squared loadings in case of the principal axis factoring, and eigenvalue in case of the PCA. So over here, the sum of the squared loading that we are getting is basically taken from here. Okay, and the last one is the sum down factors of all the components, or the sum down for all the items. That means summing the eigenvalues in case of PCA, or sum of the squared loadings in case of the PAF, that means principal axis factoring. It will give you the total variance explained. So if we go over here again, so how we are getting this total variance explained over here, this particular, the cumulative value, the total rotation sum of the squared loadings, either you sum up the eigenvalues or the sum of the squared loadings, that will give you the total variance. Now over here, I think it is also required to understand what exactly we mean by the eigenvalue, because we have come across this term several times. So what exactly is eigenvalue? So eigenvalues actually represent the total amount of variance that can be explained by a given principal component. And they can be both, theoretically, actually, if you see, sometimes you will find they can be both having positive or negative values. But in practice, since they explain variance, they are always positive in nature. So that's eigenvalue. But in some literature, you will also come across a term called the eigenvector. Now, eigenvectors are basically the weights assigned to each and every eigen. So again, I'm just repeating what is the concept of the eigenvalue. The eigenvalue actually represents the total amount of variance that can be explained by a given principal component, or can by a principal component. And as I have told you, that theoretically it is possible for an eigenvalue to assume both positive and negative value, but since it explains the variance, it is considered to be always positive. And then we have certain eigenvectors. Eigenvectors are basically the weightages that is assigned to the eigenvalues. Okay, so eigenvalues and eigenvectors are instrumental in calculating the factor loadings. The factor loadings, which are in fact the correlationship between the observed variables and the extracted factor. So what you have to report over here, you have to report the KMO and the Bartlett's test. You don't have to report communalities in a journal paper. Communalities can be reported in your thesis, PhD thesis. You have to report this total variance explained. Okay, the total variance explained over here. And one more thing you have to explain over here, which is called the common method bias, or CMB. What is a common method bias? If a single factor is explaining more than 50% of the variance, then your model is suffering from something which is called a common method bias. Okay, so let me repeat it once more. If a single factor, that means say factor 1 or factor 2, any of one factor, if it is explaining more than 50% of the variance in this particular model, then the model is suffering from something which is called the 50% or more than that. It's called the common method bias. But in this case, you see, a single factor, if we take factor number 1, it is only explaining 19.71% of the variance. If we take a cumulative effect of 2 factors, it's 34% almost. So 4 factors which are retained in this particular factor structure are explaining a total variance of 57.68%. So this particular model, on the basis of common method biasness, stands good. So it doesn't have that problem of common method biasness. Now, you have to give the scree plot. In a journal paper, it's not necessary to give the scree plot, but in a thesis, PhD thesis, exactly the scree plot is required. Factor matrix and the rotated factor matrix. The factor matrix is not required. Yes, the rotated factor matrix is required. Now you see, the important issue over here is why we require this rotation. If I can show you, we have seen it theoretically. If you allow me, I will just show one thing. If we do not rotate, okay, say rotation is none. Okay, so we are not using any kind of a rotation. So what will be the problem? The rest of the things are fine. For extraction, let us go for PAF. Okay, so we are not rotating this. So what will be the problem? Let us see. Let us go to the. This is the factor matrix. You see, since we have not rotated, we will not get the rotated part. Now, if we see the factor matrix, you see the problem for a researcher is come to this particular, say for example, item number, this one, okay, 1, 2, 3, 4, the fourth variable. You see, the factor loading in factor 1 is 0.597 and factor loading in factor 3 is 0.551. Now, as a researcher, it will be very difficult for you to assign this particular variable either in factor 1 or in fact, because you will be tempted to actually assign these variables either in factor 1 or in factor 2, or in factor 3, because these two values both are very significant, both are very high. Come to another one, say for example, this particular variable loaded in factor 1 with 0.467, loaded in factor 4 with 0.433. This variable factor 1 0.460, factor 3 0.438. It will be very difficult for the researcher to interpret the solution. What will be the interpretation? You should assign a single observed variable under a single factor. So one single observed variable should allow you to define a single factor. So there should not be any cross-loading. It will become a non-congeneric model. A non-congeneric model is not acceptable. Okay, you should try and focus on a congeneric model. So congenericity basically specifies that the observed variables are grouped into a single factor. Okay, so if this is the condition, when we have an unrotated axis, that means axes are in their original position. So now if we are tilting the axis and we are allowing the software to conduct a rotation. So let us just go back. In the rotation, we are going for Varimax and then we are continuing. So everything remaining the same. Now, you see, in the factor matrix, or basically we get the rotational matrix. You see, now it is very much interpretable. You have this particular observed variable number 1. It is having a value of 0.875. And for the other factors, the values are very negligible, 0.127, 0.176, 0.157, way below the value of 875. So you can easily take a decision and assign this particular observed variable under factor 1. Similarly, in this particular case, where we had a conflict in variable number 4, that we had two separate values which are of almost similar significance in factor 1 as well as factor 3. Now you see, after the rotation, it's 492 for the first factor, and the other values are quite insignificant, 0.144, 0.209, 0.235. So now we are relatively in a better position to dimensionalize this entire factor structure. So unidimensionality and interpretability is ensured. Now, one more thing I did not use in that analysis, I just told you I will be using at a later stage, this course. See, the options. In options, actually, if you have quite a large number of variables, you can exercise this option called suppress small coefficients. Normally, you know, for a better and a very robust kind of a model, very strong model, we need to have the factor loadings which are having a value greater than 0.60. So suppress all the small coefficients when you are checking this particular box, and when you are saying that all such values should be suppressed which are below than 0.60, and when you are continuing, And okay, so let us see what happens in the, now you see the rotated factor matrix. It is much more meaningful, isn't it? So for factor 1, we have 3 variables. This is a just identified model. For factor 2, there are 3 variables. Okay, this is a just identified model. For factor 3, there are 3 variables, just identified model. For factor 2, there are only 2 variables, 2 observed variables. It is an under-identified situation. So now the researcher has to think that whether to retain all the 4 factors or to retain actually 3 factors. Is it a 3-factor solution? See, statistically, as I have told you, all the statistically significant output does not mean that you have got a very robust model in your hand or a very strong model in your hand. So in this case, you see factor number 1, factor number 2, and factor number 3, they are having the minimum requirement of or minimum support of the observed variables. So the ideal situation would have been, for all, see, the number of variables, one of the reasons is the number of variables is too low for this. So as a result of which, whenever we are conducting the factor analysis, we say that the battery of items should be quite large. Okay, otherwise you end up with a model which is under identified, and although it is achieving statistical significance, it won't be considered as a very good model. In this case, if you are retaining a 3-factor structure model, then it is acceptable on the bare minimum ground, because you require at least 3 observed variables per identified, per extracted factor. Had it been 4 or 5, it would have been a great model. But if you are retaining a 4-structure model, that 4th factor will continue to disturb the model and will make the model very weak. Okay, so it is the discretion of the researcher. The researcher has to decide whether he or she will retain a 4-structure model, because you see, you cannot discard it outrightly, because you have received statistical concurrence for a 4-factor model. So the total variance explained is much higher compared to that of a 3-factor model. So if we see the total variance explained, and if we are retaining only a 3-factor model, you see there will be a 10% less variance being explained with the help of a 3-factor model. So this is a kind of a tightrope walked by the researcher. So you can retain a 4-structure model also. Now, one more thing that we would like to end with: what is the function of this factor transformation matrix? Okay. The factor transformation matrix as such is not very important, and it is not reported in the factor analysis output. You will not find in any journal paper or any this is the factor transformation matrix has been reported. But why factor transformation matrix is important, actually, this factor matrix, you see this particular matrix that we have got, factor matrix, and then we have got the rotated factor matrix. From factor matrix to rotated factor matrix, if we want to convert a factor matrix and if we want to get a rotated factor matrix, in between what we are having, we are having that rotation. Over here, we have used the varimax rotation or the orthogonal rotation. So between the factor matrix and the factor rotated factor matrix, the factor transformation matrix comes. Or we can say the factor matrix is converted into a rotated factor matrix through the factor transformation. So the transformation or the rotation, it takes place, and it is demonstrated or depicted with the help of this factor transformation matrix. And the off-diagonal values of this factor transformation matrix, if you take an off-diagonal value, and if you get an inverse cosine of this off-diagonal value, you will get to what degree the axis has been tilted. Say for example, the off-diagonal value is 0.692. Let me show you. If we go for a calculation, the inverse cosine calculation, 0.692, say for example, calculate. We are calculating the inverse cosine for this. So we get a 46.21. So the axis has been tilted by 46 degree to get this solution, to get this rotated component matrix. So that is the significance of this transformation matrix. So transformation matrix basically represents what happens in between the factor matrix, and it gets converted into a rotation. So what happens in that particular rotation? To what degree this? What is the angular degree that has been taken up by the rotation process to tilt the axis? So in this case, we have seen we have taken the inverse cosine of the diagonal value of that transformation matrix, and we have got the inverse cosine, and it suggests that we have got a tilt of 46.21 degrees. So it was rotated counterclockwise to the proportion of 46.21 degree to get this particular solution. Which solution? This particular solution. A four-factor solution was achieved by tilting the x and the y axis to a proportion of 46.21 degree counterclockwise. Okay, so these are the issues that you can report, but the mandatory things that you will be reporting for factor analysis is the determinant, which ensures that your correlation matrix is not a singular matrix or an identity matrix. At least there is a high degree of correlationship between the observed variables. Report the KMO and the Bartlett's test. KMO basically ensures about the sample adequacy. So any value over 0.8, it will ensure the sample adequacy that this particular data set that you have taken is adequate to conduct the factor analysis. The Bartlett's test of sphericity, which churns out the chi-square and the degrees of freedom with the significance value. It helps you to reject the null hypothesis. The null hypothesis is there is no correlationship between the observed variables. Okay, so higher the chi-square value, better will be a chance to reject the this null hypothesis. And actually, Bartlett's test of sphericity confirms that your data is amenable for factor analysis. Okay, and then you have to report the communalities. You have to report the scree plot. If you are writing a PhD thesis, obviously the scree plot has to be reported. If you are writing a paper, just state that it's a four-factor solution, and the cumulative total variance explained by the four-factor is 57.68%. You show the rotated component matrix. Okay, this is most important, the rotated component matrix. So these are all the things that you need to explain with the help of. Oh, okay, one more thing I forgot. Like when you will be explaining the total variance explained by the factors being extracted, you also report the common method biasness, CMB. So just you can say that the common method biasness in this case does not exist, because the first factor is only explaining an amount of 19%, 20% of the total variance. So the CMB is not an issue for this particular thing. Okay. Now, since we have got a very significant correlationship between the observed variables, there can be certain cases. Suppose I am dealing with only 12 variables. Suppose you are dealing with 25, 30, 40 variables. So the correlation matrix will be a huge matrix. Okay, and you need to examine the correlation matrix very carefully. Okay, because this correlation matrix will be the first output which will help you to reject certain observed variables, to filter out certain observed variables. So in the very first chance, if you find that correlationship does not exist between 3 to 4 variables, at the very outset, you just reject those observed variables from the entire data frame. Okay, because they will continue to disturb in the subsequent analysis. If you do not find significant correlation between certain observed variables, you simply delete those variables, because those if you retain those variables, it will make your ultimate model very weak. Okay, so because this EFA will develop the measurement model in future, because as I have told you at the very beginning when we were discussing the theoretical part of the EFA, we told that EFA basically is an interdependence technique. In an interdependence technique, we do not have a very pre-designated or pre-identified set of dependent or independent variable. But when you will be proceeding further after identifying the factor structure, suppose you are identifying 4-factor structure, and if a scholar now, if he or she is in a position to identify 2 factors as dependent and 2 factors as independent, and now he or she can form a structural model. So from a measurement model, when we are going for a structural model, we are converting an interdependence technique into a dependence technique. So while forming a structural model, if you retain all those variables which did not exhibit significant correlationship between each other, they will not churn out a very strong structural model. So if you want to progress further after EFA, if you want to go ahead and develop a structural equation model or a structural model, and if you test the model with the confirmatory factor analysis, so from the very beginning, try to filter out all those variables which are very disturbing and which will make the model very weak. Okay, so that is one of the issues. I have seen many scholars who have not identified it at the very beginning. You need to look through your correlation analysis very carefully. If you are finding very insignificant correlationship, or even zero correlationship, very weak correlationship between the variables, just delete those items. Okay, so you can actually go through those items. You will find that since they are exhibiting such poor correlationship between each other, probably the respondent did not find adequate, you can say, adequate information through those variables, through those statements, so whereby they can come out with a proper answer. Okay, so the vagueness of that particular thing may be one of the reasons. Okay, so that is one thing to look for. If you have a very low correlationship value, you discard it. Okay, so that brings us to the end of this particular presentation, and hopefully, Dayada, I have finished it off in time, the time that you have said. So